Look at your hands. Go on. Hold them up to the light. Turn them over. See the lines, the creases, the geography of a life lived. They seem solid, don't they? They feel real. You can clap them together, and they meet with a satisfying, definite smack. A sound that declares, I am here. This is solid. This is real. You trust this feeling. You have built your entire life upon it. The chair you're sitting in is solid. The floor beneath your feet is firm. The world outside your window is a tapestry of definite objects, each in its proper place, each obeying a set of predictable, reliable rules. This is the foundational lie. It is the most elegant, most convincing, and most necessary illusion ever conceived. An illusion so profound that you are not the audience. You are part of the performance. Your hands are not solid. They're ghosts. They are phantom clouds of agitated energy, vast empires of empty space, populated by shimmering, uncertain sparks that flicker in and out of existence. They are a storm of probability, a fleeting consensus, a temporary agreement among trillions upon trillions of tiny whispers that have, for a moment, decided to behave like a hand. What you perceive as solid is merely a statistical improbability so vast it feels like a certainty. A ghost so dense it can hold a cup. This is not poetry, not a metaphor for some spiritual truth. This is the bedrock of your physical reality. This is what the last 100 years of science have been screaming at us. A message so strange, so contrary to every instinct we possess, that we have collectively chosen to look away, to admire the technological fruits of this knowledge, while politely ignoring the terrifying, beautiful, and world-shattering implications of the tree from which they fell. We're about to look directly at that tree. We're going to peel back the veil of the concrete and the certain and stare into the abyss of the possible. What is this ghost in the machine of the universe? What is this fundamental strangeness that builds your bones and ignites the stars? It has a name. We call it a quantum, and it insists that the world you think you know does not exist, not in the way you think it does. To understand this, you must first understand the lie, the great, comfortable lie of the classical world. For centuries, this was our universe. It was a magnificent clockwork, wound by a divine hand and left to tick along with perfect mathematical precision. Isaac Newton gave us the equations for this clock. He described a universe of objects, of things. An apple was an apple. The moon was the moon. They had a definite position, a definite momentum. They followed paths we could calculate, predict, and understand. Everything was a dance of cause and effect. Simple, elegant, reassuring. This was a reality you could grasp, a reality you could put on a table and measure. Science was the process of discovering the gears of this cosmic machine, of learning its rules so that we might become its master. We built steam engines and telegraphs. We mapped the heavens and the continents. We were confident, armed with reason and mathematics, that we were on the verge of knowing everything. Then, at the turn of the 20th century, the clock began to stutter. The universe, it seemed, had a secret, a hidden life that took place in the shadows, in the impossibly small spaces between the gears of Newton's machine. It started with something as simple as light, or rather, the light from things that were hot. For years, physicists have been stumped by a problem. When you heat an object, it glows. It radiates energy. Our classical equations, the very tools that could predict the orbit of a planet, failed miserably at describing the color of this light. They predicted that any hot object should release an infinite amount of ultraviolet energy, an outcome so absurd it was called the ultraviolet catastrophe. It was as if our most trusted map of reality led directly off the edge of a cliff. The universe was telling us that our map was wrong. In the year 1900, a German physicist named Max Planck, a man deeply conservative in his scientific views, took a step he would later describe as an act of desperation. He was not a revolutionary. He was a man trying to fix a broken equation. To make the math work, he had to introduce a fudge factor, a mathematical trick. He proposed that energy was not a smooth, continuous flow, like water from a tap. Instead, he suggested it could only be emitted or absorbed in tiny, discrete packets, like currency that only comes in coins of a specific denomination, with no smaller change allowed. He called these packets quanta. He did not believe they were real. He thought of it as a bookkeeping convenience, a temporary scaffold that would be torn down once the true, elegant, classical solution was found. But the scaffold refused to be torn down. It held. His equation worked perfectly. It precisely described the light from a glowing object. It had solved the ultraviolet catastrophe. But in doing so, it had shattered the very foundation of classical physics. It had introduced a graininess, a lumpiness, to the smooth fabric of reality. It was the first whisper of the ghost. Then came a young patent clerk in Bern, a man with a rebellious mind who was already busy rewriting our understanding of space and time. In 1905, Albert Einstein took Planck's desperate trick and declared it was real. He proposed that light itself was not a wave, as everyone had believed for a century, but was actually made of these tiny packets, these light quanta, which we now call photons. This idea explained another nagging mystery, the photoelectric effect, where light hitting a metal surface could knock electrons loose. It worked as if tiny bullets of light were striking the electrons. The idea was radical. Was light a wave, or was it a particle? The evidence seemed to say it was both. How could that be? How could something be two contradictory things at once? The question hung in the air, unanswered. A paradox. And the paradoxes were only just beginning. The focus shifted from light to matter itself. The atom, once imagined as a tiny, solid billiard ball, was revealed to be a miniature solar system, with a dense nucleus for a sun and tiny electrons orbiting like planets. This was the model proposed by Ernest Rutherford, and it was beautiful, but was also impossible. According to the classical rules, an orbiting electron was a charged particle moving in a circle and should be constantly radiating away its energy. Within a fraction of a second, every electron in every atom should spiral into the nucleus, and all matter should collapse into a puff of radiation. The fact that your hand exists, that the chair you sit in is still here, is a direct violation of the physics of the 19th century. The world was stable. Our equations said it should not be. Once again, a hero was needed. He arrived in the form of a gentle Danish physicist named Niels Bohr. He was a poet of science, a man who thought in images and philosophical paradoxes as much as in equations. He looked at the impossible atom and made a decision as radical as Planck's. He simply declared that the classical rules did not apply. He said that electrons could only exist in specific, allowed orbits, like designated tracks around the nucleus. They could not exist in the spaces in between. To move from one track to another, an electron had to perform an instantaneous quantum leap. It would vanish from one orbit and reappear in another, without ever having traversed the space between them. Think about what this means. It is not like jumping from one rung of a ladder to another. It is like being on the first rung, and then, in the next instant, simply being on the fifth rung without ever having been on the second, third, or fourth. Where's the electron during the leap? The theory had no answer. The question itself, Bohr suggested, was meaningless. This was the new physics, not a description of what is, but a set of strange rules about what is allowed. It was a physics of thou shalt not radiate energy while in a stable orbit. Thou shalt not exist between these allowed states. Einstein, the man who had given the quantum its first taste of reality, was horrified. He had helped unleash this ghost, and now he saw it beginning to dismantle the rational, cause and effect universe he so deeply believed in. God does not play dice, he would later famously protest. But the evidence kept mounting. The dice, it seemed, were rolling. This early quantum theory was a mess. It was a patchwork of brilliant insights and ad hoc rules that worked, but no one knew why. It was a collection of clues, not a complete story. Then, in the mid-1920s, a new generation of physicists, young, brilliant, and unburdened by the old classical ways of thinking, blew the doors wide open. Men like Werner Heisenberg and Erwin Schrödinger did not try to patch the old theory. They built a new one from the ground up. And what they built was a cathedral of mathematics, so strange, so abstract, it seemed to have lost all contact with the physical world. Schrödinger described the electron not as a particle at all, but as a wave of probability. Imagine that the electron is not a tiny point, but a smear, a cloud of potential. The wave is not a physical wave, like in water, but a mathematical one. Where the wave is most intense, there's a higher probability of finding the electron if you were to look for it. Where the wave is weak, the probability is low. But until you look, the electron is not in any single place. It is everywhere its wave exists. It is a cloud of pure potential, a superposition of all its possible locations at once. Let that sink in. The fundamental building block of your body, the electron, does not have a definite location until it is measured, until you interact with it. It is not a thing at a place, it is a ghostly all of the above. Heisenberg arrived at the same strange conclusion from a different direction. His matrix mechanics was a stark, abstract algebra that did away with any attempt to visualize what was happening. It was pure math, and from it emerged his famous uncertainty principle. The principle states that there are pairs of properties that you can never know with perfect precision at the same time. The more accurately you know a particle's position, the less accurately you can know its momentum. And vice versa. It is not a limitation of our measuring instruments. It is a fundamental property of reality itself. The universe places a hard limit on what can be known. If you pinpoint the location of an electron, its momentum becomes a complete blur. If you measure its momentum exactly, its location dissolves into a haze that fills the entire universe. Reality, at its most fundamental level, is blurry. It is uncertain. It is fuzzy. This was the breaking point. This was the definitive schism between the old world and the new. The classical world was a world of certainty, of objects, of causes and effects. The quantum world was a world of probabilities, of waves of potential, of fundamental unknowability. This changes everything, because you're not made of classical objects. You're made of these quantum ghosts. So what are you? You're a collection of these uncertainties, a symphony of probabilities. You are made of particles that have no definite location until they are part of a larger system that measures them. You are built from components that refuse to be pinned down. The solidity you feel in your hand is the result of trillions upon trillions of these probability waves overlapping and interacting in a way that, on average, creates a stable pattern. The atoms in your hand are mostly empty space, yes, but the electron clouds of those atoms, these fields of probability, push against the electron clouds of the atoms in your other hand. What you feel is not substance touching substance. It is force fields repelling force fields. It is probability pushing against probability. You have never truly touched anything in your entire life. You have only ever felt the ghostly resistance of quantum fields. Let's dive deeper into this strange menagerie. The quantum world is not just populated by electrons and photons. Over the decades, our explorations have revealed a whole zoo of strange and wonderful entities. We needed a map, a way to categorize the strangeness. We call this map the Standard Model of Particle Physics. It's one of the most successful scientific theories ever devised, yet it reads like a catalog from a fantasy novel. The matter, the stuff that makes up you and me and the stars, is built from two families of particles, quarks and leptons. Let's start with the leptons. The most famous lepton is the electron, the tireless ghost we've already met. But it has two heavier, unstable cousins, the muon and the tau. They are identical to the electron in every way except for their mass. They are phantoms of the electron, appearing for fleeting moments in high-energy collisions before decaying back into lighter particles. Why are there three of them? Why these specific masses? No one knows. They are simply part of the recipe. Then there are the neutrinos. The neutrinos. They are the ultimate ghosts. They are so light, so weakly interacting, that they can pass through the entire Earth without touching a single atom. Trillions of them are streaming through your body right now, fired from the heart of the sun, and you do not feel a thing. They are whispers of reality, carrying information across the cosmos, almost entirely unseen. They too come in 3 flavors, one to partner with each of the other leptons. That's one half of the family of matter. The other half is, in some ways, even stranger. The quarks, the protons and neutrons that form the nucleus of every atom, the very heart of matter, are not fundamental. They are composite particles. They are tiny prisons, each containing 3 quarks. And the quarks themselves are bizarre. They come in 6 flavors, given whimsical names: up, down, charm, strange, top, and bottom. All the stable matter in the universe is made from just the 2 lightest, the up and the down. A proton is 2 ups and a down. A neutron is 2 downs and an up. The other 4 are like the heavier leptons, exotic, unstable, and only seen in the debris of violent particle collisions. But here is the truly strange part. You can never, ever see a quark by itself. They're condemned to a life of permanent confinement. This is not a technological limitation. The universe itself forbids it. The force that holds quarks together, appropriately called the strong nuclear force, has a unique and baffling property. Unlike gravity or electromagnetism, which get weaker with distance, the strong force gets stronger. Imagine 2 quarks connected by a magical rubber band. As you pull them apart, the energy in the band increases. If you pull hard enough, the band doesn't just stretch further, it snaps. But when it snaps, so much energy has been poured into it that the energy itself converts into mass, following Einstein's famous E equals mc squared. A new quark and antiquark pair springs into existence from the void, and each new particle immediately partners with one of the original quarks. You started with 1 rubber band and try to break it. You ended up with 2. Try to isolate a quark, and you will only ever create more quark-filled particles. It is a perfect, inescapable prison. The very act of looking for one creates the walls that hide it. So how do we know they are there? We see their shadows. We see their fingerprints. In the 1960s, at the Stanford Linear Accelerator Center, scientists fired high-energy electrons at protons. They expected the electrons to pass through the protons as if they were soft clouds of charge. Instead, some of the electrons bounced back sharply, as if they had struck something small, hard, and real inside. We see the evidence of the prisoners rattling their cages, but we can never see the prisoners themselves. Are they real? What does real even mean for something that cannot, by the laws of nature, ever be isolated and put on a scale? They are a necessary part of the explanation. They are a confirmed prediction of the mathematics. Their existence is a truth inferred, not a truth directly observed. They are ideas confirmed by shadows. And what about the forces? The pushing and pulling that holds this whole phantom circus together? In the quantum world, forces are not some mysterious, invisible influence. They are an exchange. They are a conversation. Every force is carried by a particle. These are the bosons. The electromagnetic force, the one responsible for light, electricity, and the fact that you can't walk through walls, is carried by the photon. When 2 electrons repel each other, what is actually happening is that they are exchanging photons. It's like 2 skaters on an ice rink throwing basketballs at each other. The exchange of the balls pushes them apart. The strong nuclear force, the one that glues quarks together inside protons and neutrons, is carried by a particle called the gluon. There are 8 different types of gluons, and they're the source of that strange, unbreakable rubber band. They are the wardens of the core prison. The weak nuclear force, a more subtle force responsible for certain types of radioactive decay, like the process that allows the sun to shine, is carried by the massive W and Z bosons. So you have the particles of matter, the quarks and leptons, and you have the particles of force, the bosons. This is the cast of characters, but the play they are performing is where the true madness lies. Let's go back to that electron, that wave of probability, that cloud of what might be. Imagine an experiment. It is the most famous experiment in all of quantum physics, and it contains the central mystery. It is called the double-slit experiment. You have a barrier with two thin, parallel slits in it. You fire something at the barrier, say tiny pellets from a paintball gun. Some pellets will be blocked, some will go through the left slit, some will go through the right. On a screen behind the barrier, you will see two distinct bands corresponding to the pellets that made it through the two slits. Simple. Now, you do the same thing with waves. Imagine ripples in a pond. As the waves pass through the two slits, they spread out and interfere with each other. Where a crest meets a crest, you get a bigger wave. Where a crest meets a trough, they cancel out. On the screen behind, you don't get two bands. You get a complex pattern of many bands, an interference pattern. This is the unique signature of a wave. Now we fire electrons, one at a time. An electron is a particle, right? A tiny speck of matter. So we should expect to see two bands on the screen, just like the pellets. So we fire one electron. It leaves the gun, flies to the barrier, and makes a single dot on the screen behind it. We fire another dot. We keep doing this for hours, firing one electron at a time, so there is no possibility of them interfering with each other. Slowly, as thousands of individual dots build up, a pattern begins to emerge. And it is not two bands. It is an interference pattern. Read that again. The electrons, fired one by one, with nothing to interfere with, are arranging themselves into the pattern of a wave that has interfered with itself. This is impossible. It is a logical contradiction. How can a single particle, traveling alone, interfere with itself? The only way for an interference pattern to form is if the electron went through both slits at the same time. The particle behaved like a wave. It passed through both slits simultaneously as a cloud of probability. Its own potential paths interfered with each other, and this interference guided the particle to a specific point on the screen. The single electron knew about both slits. It was aware of the entire experimental setup. This result is so bizarre that physicists, naturally, refuse to believe it. They said, "Okay, we will catch it in the act. We will place a detector at one of the slits to see which path the electron actually takes." So they do. They set up a tiny detector, a little puff of light, that will tell them if the electron went through the left slit or the right slit. And now, the universe plays its trump card, the ultimate act of cosmic mischief. They fire the electrons again, one at a time. The detector works perfectly. For each electron, it says, this one went through the left slit, this one went through the right, left, right. Now they know the path of every single particle. They let the experiment run for hours, building up the pattern of dots on the screen. And the interference pattern vanishes. It is gone. In its place are just two bands, exactly as you would expect for particles. The very act of observing which path the electron took forced it to behave like a particle. The moment you looked, the electron had to make a choice. It had to abandon its ghostly wave-like state of being in multiple places at once and collapse into a single, definite reality. The wave of potential, the superposition, was destroyed by the act of measurement. Reality changed because it was being watched. What does this mean? It means the universe is not a movie that plays out independently of the audience. The observer is not a passive spectator. The observer is a participant in the creation of reality. Your act of measurement, your act of knowing, forces the universe to commit to a story. Before you look, the electron is pure potential. A question: where am I? When you look, you provide the answer. You are here. This is the measurement problem, and it is the pulsing, philosophical heart of quantum mechanics. It is the point where physics collides with questions about consciousness, reality, and the role of the mind in the cosmos. Who, or what, counts as an observer? Does it have to be a conscious human? A physicist in a lab coat? Or can it be a camera? A rock? An air molecule that bumps into the electron? The line is blurry, but the implication is staggering. The world out there is not a fixed, pre-existing thing. It is a dance between potential and actuality, a dance choreographed by the act of interaction. And the dance gets stranger still. If superposition, the idea of being in many states at once, shatters our notion of a single reality, then entanglement obliterates our understanding of space and connection. Einstein, who was never comfortable with the probabilistic nature of quantum theory, devised a thought experiment with two of his colleagues, Boris Podolsky and Nathan Rosen, to expose what he believed was an absurdity at its core. It became known as the EPR paradox. But instead of showing quantum mechanics to be incomplete, it revealed its deepest and most unsettling secret. Imagine you create two particles, say, two electrons, in a special linked state. They're created together and fly off in opposite directions. This linked state has a specific property. Let's say the particles have a quantum property called spin, which you can think of as being either up or down. The linked state dictates that if one particle is measured to have spin up, the other must, at that exact same instant, have spin down. And vice versa. They are anti-correlated. This doesn't sound so strange at first. It's like putting one black glove and one white glove into two separate boxes and mailing them to opposite ends of the earth. When your friend in Australia opens her box and finds a white glove, you instantly know that you have the black one. There's no mystery. The information was always there, predetermined from the moment the gloves were packed. But quantum mechanics insists that this is not what is happening. Remember superposition. Until it is measured, the electron spin is not determined. It is not secretly up or down inside its box. It is in a superposition of both up and down simultaneously. It is a 50-50 probability cloud. So you have two of these probability clouds, these entangled ghosts, flying apart, perhaps to opposite sides of the galaxy. Neither particle has a definite spin. They are both in a state of pure potential. Now, you measure one of them. You open the box here on Earth and find that its spin is up at that exact moment, instantaneously faster than the speed of light. The other particle, light years away, abandons its state of superposition and collapses into a definite state of down. The measurement of one particle instantly affects the state of the other, no matter how far apart they are. This violates what Einstein held most sacred, the principle of locality. The idea that no influence can travel faster than the speed of light. This seemed to him like spooky action at a distance. It was a form of cosmic telepathy, a ghostly connection that defied the known limits of the universe. He was convinced that the particles must have had hidden properties, like the gloves, that determined their states from the beginning. He was sure that quantum mechanics was an incomplete theory, a blurry approximation of a deeper, more deterministic reality. For decades, this was a philosophical debate. Bohr argued that the two particles were never truly separate. They remained part of a single, indivisible quantum system, a single mathematical wave function, no matter how far apart they were. Asking what the spin of one particle was before measurement was a meaningless question because it didn't have one. The system had a property, but the individual parts did not. Then, in the 1960s, a physicist named John Bell devised a mathematical theorem that could actually test the question. It was a brilliant piece of logic that could distinguish between Einstein's hidden variable world of gloves and Bohr's strange world of non-local connection. Experiments were performed, again and again, and every single time, Einstein was wrong. The universe is spooky. The connection is real. It is instantaneous. It is a fundamental feature of reality. What does this mean? It means that, at some fundamental level, the universe is not a collection of separate objects. It is a single, interconnected whole. The two particles are not two things. They are two aspects of one thing. The space between them is an illusion. You are made of particles that were forged in the hearts of stars billions of years ago. Are you still connected to them? Are the atoms in your left hand entangled with the atoms in a distant galaxy? The theory suggests it's possible. The universe is a vast, tangled web of these ghostly connections. Every interaction creates new entanglements. We are woven into the fabric of the cosmos in a way that is far more intimate than we could have ever imagined. You're not in the universe. You are the universe. The separation is an illusion of scale and perception. So let's take stock. We have a reality built from particles that don't have definite properties until they're measured. We have a universe where looking at something changes it. And we have a cosmos laced with faster-than-light connections that bind its distant parts together into an inseparable whole. This is the world described by the equations. But what does it mean for us? For our experience of reality? This is where physics ends and philosophy begins, a blurry boundary where our deepest questions about existence reside. If reality is only made definite by measurement, what was the universe doing before there were any observers? Before there was life, before the first conscious mind flickered into being? Was the entire cosmos a vast, undifferentiated ocean of quantum potential? A superposition of all possible histories, all possible states, waiting for a participant to collapse it into a single story? This question led physicists down one of the most mind-bending paths of all, the many-worlds interpretation. In the 1950s, a physicist named Hugh Everett III, a student of the great John Wheeler, looked at the measurement problem and proposed a radical solution. He asked, what if there is no collapse? What if the wave function never breaks down? What if, when you measure the electron spin, the universe itself splits in two? In one universe, you measure up, and in that universe, there's a version of you who is now certain of that result. But at that same moment, a second, parallel universe branches off. In that universe, a perfect copy of you measures the spin as down and is just as certain of their result. Every quantum measurement, every probabilistic event, from the spin of an electron to the radioactive decay of an atom, causes reality to cleave into multiple parallel streams. All possible outcomes of any event not only can happen, but do happen in their own separate, non-communicating universes. There is a universe where you turned left this morning instead of right. A universe where you took that other job. A universe where you said the thing you wish you had said. There are countless versions of you, living out every possible permutation of your life, spinning off into an infinitely branching tree of realities with every passing moment. It is an idea of breathtaking scope and audacity. It solves the measurement problem by simply getting rid of the collapse. The mathematics of quantum mechanics is taken at its word. It describes a constantly splitting reality. There is no special observer. The interaction simply entangles the observer with the particle, creating branches of the universal wave function where each outcome is realized. Is this science or science fiction? The theory is mathematically consistent. It makes no testable predictions that differ from the standard interpretation, so we cannot prove it right or wrong. It is a matter of interpretation, of philosophical taste. Do you prefer a single universe where reality is conjured into being by observation, or an infinite multiverse where everything that can happen does happen? Either way, the comfortable, singular, solid world of our intuition is gone. It is replaced by either a participatory reality we help create moment by moment, or an unimaginably vast multiverse of which our entire existence is but a single, fragile branch. Which brings us to the final, deepest mystery, the one that links all the others. The mystery of you. Consciousness. Is it just a coincidence that the structure of reality seems to depend on observation? Is it just a quirk of language that we use words like information, measurement, and knowledge to describe the behavior of subatomic particles? Or is there a deeper connection? For decades, this was a taboo subject in physics, a question to be swept under the rug. But the ghost at the heart of the quantum world refuses to be exorcised. The observer problem will not go away. What if consciousness is not an accidental byproduct of complex brain chemistry? What if it is not an emergent property that arises from firing neurons, like wetness arising from water molecules? What if consciousness is something more fundamental? This is a speculative leap, a journey into the uncharted territory where science, philosophy, and spirituality converge. But it is a leap that some of the greatest minds in physics have been tempted to take. John Wheeler, the man who coined the terms black hole and wormhole, and who was Bohr's great disciple, came to believe in what he called the participatory universe. He argued that the universe and the observer are inextricably linked. Information, he said, is the most fundamental aspect of reality. Not matter, not energy, but bits of information, answers to yes/no questions. He proposed a thought experiment. Imagine a distant quasar, a galaxy billions of light years away. Its light travels for eons across the cosmos. On its way, it passes a massive galaxy, and the gravity of that galaxy acts as a lens, bending the light, so it can take two different paths to reach Earth. Here on Earth, billions of years later, an astronomer sets up a telescope. She has a choice. She can either set up her equipment to determine which path the light took, or she can set it up to recombine the light from both paths to create an interference pattern, just like in the double-slit experiment. If she chooses to measure the path, the light is forced to have behaved like a particle and to have taken one specific route around the lensing galaxy. If she chooses to look for interference, the light must have behaved like a wave and taken both paths simultaneously. But the choice of which path to take was made billions of years ago. Her choice, made in the present, seems to reach back in time and determine the history of a photon that began its journey long before the Earth even formed. Wheeler's conclusion was breathtaking. He said, "We are not just observers of the past. We are participants in its creation. The universe does not exist out there, independent of us," he wrote. "We are inescapably involved in bringing about that which appears to be happening." The universe, in this view, is a self-observing system. It gives rise to conscious beings, and those conscious beings, through their acts of observation, give reality to the universe's past. It is a vast cosmic feedback loop, a story the universe tells about itself through us. Does this mean your mind is reaching out and collapsing wave functions? Perhaps not so directly, but it raises the question of what makes a measurement. Bohr argued it was any irreversible interaction with a large classical system. The information becomes recorded, definite. But where does that chain of interaction stop? The photon hits a detector. The detector sends an electrical signal. The signal goes to a computer. The computer displays it on a screen. The light from the screen enters your eye. It hits your retina. It triggers a cascade of neural signals in your brain. At what point in that chain did the collapse happen? At what point did the potential become actual? Many believe it happens at the first stage, the interaction with the detector. But some, like the physicist Eugene Wigner, argued that the collapse is only truly complete when the information enters a conscious mind. Until then, the detector, the computer, and the eyeball are all just part of one giant, entangled quantum system, all in a superposition of states, until a mind apprehends the result. In this view, consciousness is the ultimate measuring device. It is the loom upon which the threads of quantum potential are woven into the tapestry of a definite reality. We're the place where the universe becomes aware of itself. Think of what you are. You are a biological machine of unimaginable complexity. But what is that machine made of? Cells. And the cells are made of molecules. And the molecules are made of atoms. And the atoms are made of protons, neutrons, and electrons. And the protons and neutrons are made of quarks and gluons. You are, at your foundation, a swirling, seething cloud of quantum phenomena, an intricate dance of probability waves and spooky connections. You are not a machine made of little billiard balls. You are a stable, self-sustaining pattern in the quantum foam, a standing wave in the ocean of potential. Could it be that consciousness itself is a quantum phenomenon, an emergent property not of classical chemistry, but of the quantum coherence within our own brains? This is the controversial but tantalizing field of quantum biology. Scientists are finding that quantum effects like superposition and entanglement are not just confined to the pristine, cold environments of a physics lab. They're at work in the warm, wet, messy world of living things. Photosynthesis, the process that powers most life on Earth, seems to use quantum coherence to find the most efficient path for for energy to travel. The sense of smell may rely on electrons' quantum tunneling between molecules. The navigation of birds may be guided by a quantum compass in their eyes, using entangled electrons to sense the Earth's magnetic field. Nature, it seems, has been a master quantum engineer for billions of years. If these effects are at work in the basic processes of life, is it such a stretch to imagine they are at work in its most complex expression? Is your brain not just a classical computer processing bits of information, but a quantum computer exploring a vast superposition of thoughts and possibilities before collapsing into a single conscious experience? Is a thought a collapse of a wave function? Is a choice the universe branching? These are questions at the farthest frontier of our knowledge. We do not have the answers, but the questions themselves change us. They dismantle the walls between the inner world of our experience and the outer world of physical reality. The old story was simple. There was a material world, and then there was consciousness, the subject and the object, the seer and the seen. A clean, neat division. Quantum mechanics erases that line. It suggests that the seer and the seen are part of a single, dynamic process. That reality is not a noun, but a verb. It is something that is happening, not something that just is, and you are at the heart of that happening. So let's return to the beginning, to your hands. They are not solid. They are an event, a process, a stable harmony played on the strings of quantum fields. They are woven from the uncertainty of the quantum realm, held together by forces that are conversations between particles and connected by invisible threads of entanglement to the farthest reaches of the cosmos. The world is not a collection of things. It is a network of relationships. This can be a terrifying thought. It pulls the rug of certainty out from under our feet. It dissolves the solid world we have clung to for comfort and replaces it with a shimmering, probabilistic ghost. Not a thing, not a certainty, not an answer, but a question. But it is also a profoundly liberating and beautiful thought. It means you're not a stranger here. You're not a ghost in a machine. You are a part of the fabric of the universe, a node in its cosmic network of information, a participant in its ongoing act of creation. The laws of physics are not just external rules that govern you. They are the internal grammar of your own being. The stardust in your veins is not just a poetic phrase. It is a literal truth, and that stardust is still humming with the quantum weirdness of the Big Bang. What is real? Is a quark real if it can never be seen? Is a parallel universe real if it can never be visited? Is a potential real before it is actualized? Perhaps the question is not what is real, but what is it possible to experience? Reality is not the cold, hard, objective thing we once thought it was. It is a subtle, fluid, and mysterious poetry, written in the language of mathematics. And we're just beginning to learn how to read it. We are a way for the cosmos to know itself. We are the universe's sensory organs, the point at which the vast ocean of potentiality crystallizes into the jewel of a single, lived experience. Look around you now, at the light, the colors, the shapes. Do not see them as solid, separate objects. See them for what they are, a momentary consensus, a fragile truce in a war of probabilities, a wave on an infinite ocean. And know that the very act of your seeing, your awareness, is the chisel that gives this fluid world its form. You are not just looking at reality. You are in conversation with it. And what is it saying back to you? It is whispering a secret that has been waiting billions of years to be heard. That you are more mysterious than you know. That you are more connected than you can imagine. And that the boundary between you and the universe is a beautiful, necessary illusion. You're not a drop in the ocean. You are the entire ocean in a drop.